I'm all good. All right, hi everybody. I'm Mike Tutkowski. I am going to be talking about primary storage mainly in CloudStack today. And just like John, if you guys have any questions, just feel free to raise your hand or inject any time along the way. Just kind of want to make sure it's as interactive as we can make it. In particular, what I'm going to be talking about is guaranteeing performance of primary storage in CloudStack. And we'll see how that turns out in a little while as we make our way through the deck here. So I'm I'm full-time on CloudStack. I work for a company in Boulder, Colorado called SolidFire. We develop a distributed storage area network technology that's based on an all-flash array, all-flash architecture rather. The main point for the SolidFire SAN is to guarantee quality of service. So in our model, this translates into setting minimum, maximum, and burst number of IOPS. So we'll see as I make my way through how this translates into CloudStack. But the idea here is to be able to spin up a VM and have your root disk, have your data disk, have predictable performance. So normally in a cloud environment, you don't know who your neighbors are. If the cloud is seeing a lot of activity one day, your performance in a general cloud environment may not be so great. But the next day, maybe the activity is lower and your performance is great. It's just it's variable from day to day. And so the idea behind the SolidFire SAN and how I've integrated this into CloudStack is to gain performance predictability from day to day, to know what your minimum IOPS are going to be, perhaps be able to top somebody out at a maximum, but be flexible enough for bursty workloads to even bump above that maximum when you need to. So a lot of this will just become more clear as I kind of get into this. But anyways, as we mentioned before, I'm full-time on CloudStack. So the main thing with CloudStack that I'm concerned with is quality of service. And the big issue with CloudStack is that it was never really, from my point of view at least as a storage guy in the performance area, is that CloudStack was never really architected for quality of service. In a lot of existing clouds, we have our root disks and our data disks sharing back-end volumes. So you might have a large LUN on the back end, and it's servicing a lot of root disks, a lot of data disks. And there's no real way of controlling the performance to any one of those virtual disks. And it is a simple way to design primary storage in CloudStack. But if you want to guarantee quality of service, it's not very easy to do it in that kind of a model. And so I spend a lot of my time trying to bring CloudStack into sort of a quality of service era. Anyways, so I'm on the CloudStack Project Management Committee with John. And as I mentioned, full-time CloudStack. So SolidFire has me completely on CloudStack doing this kind of work, talking to customers, helping them figure out their cloud environments with CloudStack and how to use SolidFire in that environment. A few other points here before we get into, just to give you a background kind of where I'm coming from. As I mentioned, so this is an all SSD architecture. The main reason for that choice is so that we can have predictable latency for every I/O. It's impossible really to guarantee quality of service if you have any kind of spinning media. So it's not so much for the raw speed of the SSDs. Yes, this is it's a fast system, but we use the SSDs more to guarantee predictable performance. So you might have some fast volumes, some slower volumes. You can control that on a volume by volume basis. And the way that we do this at the very lowest level is by utilizing SSDs. Yeah, and then of course the big question a lot of people ask is, well, doesn't that make it super expensive if it's an all-flash array? Well, we have very sophisticated compression, deduplication, and thin provisioning techniques, which bring the cost per gigabyte to be down on par with traditional hard disk-based systems. So a lot of times it ends up being $2.50 per gigabyte, depending on the size of the system. So it's very cost-effective as well. And then the last point here, which is really important to me as a CloudStack developer, is that the system, the SolidFire system, it was built with automation in mind from the beginning. So there's a REST, I like to call it a REST-like API that is used to automate all of the different aspects of the system. So if anybody is writing an application that utilizes the SolidFire SAN, including myself as a CloudStack developer, I'm using the same API as any of our customers would. And that's one of the ways that I interact with CloudStack. Now, as I mentioned, CloudStack was never really designed with quality of service in mind, so I do end up doing a lot more than writing a plugin for CloudStack that just happens to be based on SolidFire technology. I have to redesign a lot of the storage components to make use of that kind of storage in the first place. And a lot of this, again, it'll become more clear as we go through the decks here, but feel free, again, interrupt at any time, ask away. I'm happy to answer questions as we go. So John, he kind of asked around before to see what people's experience levels were with CloudStack, and so I don't think, I mean, I know this is a pretty basic diagram if you're really familiar with CloudStack, but it sounds like there's plenty of people in the room who are not necessarily super familiar with CloudStack terminology. So let me just kind of step through this diagram really quickly. And right now we're on version 4.4, just for context. 4.4 is GA. This particular picture, and we're going to go from pre-4.2 to 4.2 and beyond, the big change in storage came about in the 4.2 release. And so I just wanted to contrast that with what was there before. So this is prior to 4.2. As John mentioned, secondary storage lives out in that zone area. What we're going to focus on for my presentation is primary storage. And in this particular diagram, so we see we've got our zone, which is basically our data center, our pod, which we could look at as like a rack in our data center, and then our cluster, which could be vSphere, KVM, Xen server, some kind of a hypervisor cluster. Traditionally, and I guess when I say traditionally for storage, I mean prior to the 4.2 release, primary storage was exclusively at the cluster level. So you have all of your hosts in that cluster. They might have their own local storage, which can be consumed by CloudStack as primary storage, and or they can actually access shared storage, of course. Typically, in an environment like vSphere, if you have a shared LUN, if any one of those ESX servers can see that LUN, they all can see it. So we have kind of these two models of local storage and shared storage. The big difference once we hit the 4.2 release, besides the fact that vendors can now write plugins for CloudStack, which they really couldn't do prior to the 4.2 release, the second big enhancement is that primary storage, although it can still live at the cluster level, it actually has been brought out as well to the zone level. And actually my SolidFire plugin makes use of that, and we'll kind of understand why I do that as we go on here. It's not readily apparent why that might be useful in the beginning, but there is actually a very fundamental difference with the SolidFire plugin in that we don't actually create LUNs ahead of time in a static fashion. We create them as we need them in CloudStack. So this is the first time that we've ever been able to spin up VMs, and the root disk for that VM, it didn't exist on a back-end volume until that VM was spun up. So now we can go through this plug-in architecture and some of the other changes I've made to the storage framework and dynamically create and delete LUNs on the back end. So the zone level primary storage, in my case, is really representative of the SAN. So the SAN, in this case, it's a clustered scale-out system, in a sense similar to what John mentioned, where you have industry standard nodes. They're running SolidFire software. You can scale them from 4 to 100 nodes. It's all done non-disruptively as you add or remove nodes. Everything is redistributed and evenly balanced from a capacity and an I/O standpoint, transparent to the hosts that are accessing it. And so in my case, I'm actually integrating as primary storage that lives at the zone level, and then as we need LUN, create them, and then give them to the hosts in the cluster. All right. Probably, I think John covered a lot of this pretty just fast. I'll just go through this again. Primary storage versus secondary. referring to is like storage for ISOs, templates, and backups. Sometimes I guess we use the term snapshot in CloudStack, but I tend to look at that really as like a backup. You've actually taken that off the primary media and you've moved it to some secondary media. So in my mind, that's more of like a backup. And then primary storage is storage for your root disks, your data disks, a lot of high change content, typically smaller I/O sizes, random access versus sequential access for secondary storage. I think this is probably pretty clear to everybody in the room at this point based on what we've seen today. So I'm going to move on here and just sort of describe, again, kind of contrasting what we have in the 4.4, 4.3, 4.2 releases, which is post this new storage framework, with what was before it in the pre-4.2 era. So the pre-4.2 era of CloudStack, which is completely there today, you can still do all of this stuff today, but it was very static versus what we've gone to now in the 4.2 and subsequent releases. And so just to kind of drill this in a little bit, I'm going to walk through the way you would set primary storage up in CloudStack prior to the 4.2 release, and then again, this is still completely usable today if you're setting up primary storage in CloudStack. But the point to note here is that it's very static. You pre-create volumes or LUNs, whatever you want to call them, on the back-end system, which is actually that first line there. Well, really, I've already mentioned some of those things. Primary storage is associated with a cluster, just to kind of give everybody on the same page here. The cluster can access more than one primary storage. As I've mentioned, it can be local storage, it can be shared storage, it can be a combination of both. And then, as I've said, the primary storage is typically for root and data disks, as opposed to things like templates and ISOs and things like that. And then depending on your hypervisor type, it really makes a difference how primary storage is consumed in CloudStack, whether it's XenServer or vSphere or KVM. And what I'm going to go through here is actually the process of setting it up in XenServer, just because that's the most common hypervisor in CloudStack at the moment. But a lot of this is actually very similar to vSphere. KVM is a little bit different than XenServer and vSphere when it comes to setting up and consuming that primary storage. But as I kind of move forward here, we'll see how static this process is and how inflexible it really is for quality of service. And then we'll see how that we're going to take that and make it more dynamic, make it more QoS friendly. So typically what somebody might do is an admin comes along, they want to create a really large volume on a SAN or a large NFS share. Maybe, if you're on a SAN, maybe 8 terabyte LUN, something like that. So the admins actually had to go to that system, create that volume before they go over to their hypervisor, in this case XenServer, and consume that LUN. So if we're talking XenServer, what you're going to do is you're going to create a shared storage repository on that LUN. So now you've gone from one system, you've gone from that back-end system. If it was SolidFire, you've gone to the SolidFire GUI, you've created your LUN. Then you've come over to a completely different system, XenCenter, to interact with XenServer, and you've consumed that LUN as a storage repository. And once you've done that, now you're able to go over into CloudStack and create primary storage that consumes that storage repository. So it's all of this kind of pre-planning. Create the one object on the storage system, go to the hypervisor, consume it. Once that's ready, come over to CloudStack. Kind of a very static process there. Once you've got that consumed in CloudStack as primary storage, that's when you go and you make your service offerings, like your compute or your disk offerings. And again, I'm not sure how familiar everybody is with those kind of that kind of terminology with CloudStack, but a compute offering is really what defines, it's like the template for your virtual machine. So you say how many virtual CPUs you want, how much memory, things like that, basically. You can even then tie it into particular characteristics of storage. So when you imported your storage repository as primary storage, you can do things like tag the primary storage. Basically, give it some labels that describe it. If it's SolidFire and it's all SSD, maybe you could just describe that primary storage as fast or SSD. Or you can do multiple things. You can say fast, comma, SSD. And those things later can be referenced from your compute offerings and your disk offerings to kind of help, well, not really help, it basically guides CloudStack into figuring out where to put those root disks or those data disks that you create. If you say in your compute offering you want that root disk to end up on some primary storage that describes itself as fast, it could be as generic as that, or it could be really specific. It could just be, I want this root disk on SolidFire. If you have primary storage that describes itself as SolidFire, that will help CloudStack figure out where to put that root disk or the data disk. So anyways, that kind of gives you the gist as to how you go about setting up storage prior to the 4.2 release. And again, it still works today. People do this very commonly. But it is a very static process. When you spin up VMs or you create data disks from disk offerings, they can be placed on that same large LUN. So they share that LUN with essentially neighbors. You don't know if those are people from different companies. You just don't know who's on that LUN with you. You don't know what kind of activity they're going to have from day to day, which makes your performance somewhat unpredictable. And so that's the thing we want to get away from in the post, well, really 4.2 and post releases, is to have the ability to have a one-to-one mapping. So if you create a virtual disk, it's a root disk, we want that backed by a single LUN on the back end. Same thing for data disks. The ability to have a one-to-one mapping between your virtual disks and your back-end volumes. And then if you have a tool like SolidFire, you can configure those back-end volumes to have a set number of IOPS. And then you can, it depends if you're doing this in-house or if you're a cloud service provider, you can pass those kind of offerings on to your customer. Your customers may even be, if you're a large enterprise, you may treat your business the way a cloud service provider treats its customers. The different departments and the people who utilize the IT resources, they can spin up their VMs and create their data disks based on the compute offerings and the disk offerings that the IT guys in-house have created, the same way that a cloud service provider would do, and then offer that out to its customers. So really just the difference between a public and a private cloud, and this applies to both. So, but I'll dive into that in more detail later just to show a little bit more concretely how that works. But right now we're seeing that we do not have that ability. We have this statically created LUN on the back end. It's really large, and we're sticking a whole bunch of virtual disks on it, and they're just kind of competing with each other for IOPS. If you have a noisy neighbor, it's going to impact your performance. And if you, for some applications, that's okay. And for others, it's not. It just depends on your use case. So let's go ahead and make this a little bit more concrete. I'm going to walk through these steps, and we'll see what I actually just kind of talked about a second ago. And I'm going to use the SolidFire system, obviously, as a template here, just for illustrative purposes. So that first step in kind of the old storage world was go off to your storage system, create a volume, a LUN, whatever you want to call it. And in this case, I'm in the SolidFire GUI. We'll see familiar things like what's the name of the volume, how large do you want this volume to be, and then there's some unique items in this particular situation. So the SolidFire SAN was built from the ground up to be used in multi-tenant environments. So whenever you create a volume, you associate it with an account. So you could have accounts Coke and Pepsi, and the one can't see the other, vice versa. So that's one thing to kind of note here. The area that's even more interesting is the bottom area, which talks about IOPS. So we'll have, in this case, the ability to set the minimum IOPS, the maximum, and then what we call a burst. So minimum is pretty much what it sounds like. If you're pushing the system hard enough, you'll hit the minimum IOPS. And we can see here there's a scale. It's sort of normalized over 4 kilobytes. But then if you know your average I/O is, whatever, 16 kilobytes, you can see, well, instead of the 15,000 IOPS at 4 kilobytes, you're getting 5,556 IOPS, just to give you an idea of how that kind of translates from one I/O size to another. But the minimum is what it is. If you push the system hard enough and you haven't over-provisioned IOPS on the SAN, which you can do, you'll get that minimum number of IOPS. The maximum is sort of like rate limiting, but burst makes it more flexible, where if you have, sort of this works on a credit-based system. So if you're not pushing the system hard enough to hit your maximum all the time, you're accruing credits. And then if the time comes in your workload where you want to burst above that maximum, you can do so as long as there's resources available on the SAN, and you'll sort of expend those credits. And once you've expended them, you'll be reeled back down into your maximum. So min-max burst, minimum guaranteed number, maximum is sort of like rate limiting, burst makes it more flexible than rate limiting. But if you were setting this all up kind of manually prior to the 4.2 release, you would have to go into the GUI here or its API, set these numbers, probably make a fairly large LUN, and once you have that, we can go over to our hypervisor and actually consume it. Yeah?
Is there a performance penalty for the old school cluster size emulation?
Oh, it's taken into account.
Oh, it is?
Yeah. Usually people will pick the enable 512-byte emulation for like vSphere. Yeah. Natively, we do 4 kilobytes internally.
Okay.
Yeah. And NFS?
Is that a fast underneath?
No, we have a custom file system that we use to store the data. Yeah, you can think of it like a log structured file system. So the SSDs are basically being evenly worn. That's one of the big. For example, we use all consumer grade SSDs. So if you see something like, I don't know, like Extreme IO, I know they push enterprise grade SSDs, and it seems like that's the big thing for them. But most ground up flash players like SolidFire, they've designed their architectures from the ground up to play nicely with consumer grade SSDs. And so we guarantee them for 5 years, the SSDs. Yeah. So yeah, definitely that's also one of the ways that by wear leveling the way we do, we're able to obviously use cheaper SSDs. And all of the data is replicated across the cluster. So you can basically have a cluster of, let's say, 50, it goes up to 100 nodes, but let's say you got 50 nodes. You can lose any one of those nodes. The whole node worth of SSDs can go offline, and the outside world won't know about that. It's completely transparent. So what happens there is, if the SSDs have been deemed dead for a long enough period of time, we'll rebuild redundancy. In a sense, it's very much like REAC, except for REAC is object storage, and we're doing this at the block layer. And so once one of those, even just one SSD dies, we'll take the data content that was on it, which is actually spread across the cluster, and we'll regain redundancy, which usually happens within about 5 to 15 minutes for a single SSD. If you lose an entire node, you're probably looking at about 30, 45 minutes to regain redundancy across the cluster.
The IO size is done now.
So what you're doing here is you're kind of picking. You might want to look at your workload and say, well, my workload, this particular application is doing 256 kilobytes on average. Well, in that case, if I picked this 15,000 number, that's for 4 kilobyte IO, so you'd really get 500 IOPS for that 256 average.
You've got to select your IO size.
Yes, so you would want to do that based on what you know to be and you can, it's a good, that actually kind of gets me into the next point here is, let's say you pick wrong and you actually you're always hitting your max and you'd like to bump it up. It's easy to do. I mean, you can literally either go into the GUI here, our API, or through CloudStack, and you can change those numbers. There's no redistribution of data to make that happen. It's just all done online, and you bump that number up within a few seconds. As long as you're pushing the system hard enough, you'll have access to those additional IOPS. Yeah. So this is a good question. Anything else? Yeah.
How do you, if you're, say, writing at full throttle, determine whether you're running at max or at burst?
Oh, okay. So you can, let's just say you start up your application, it's consuming the volume, it's just pushing it to max right away. If you're always at maximum, you're not really accruing any credits. We kind of give you it's like credit for not hitting your maximum. And so if you do go below your maximum, you start accruing credits, and which is typically more common. People will probably be somewhere between their min and their max. They'll accrue credits, and then a database transaction happens or something like that. So instead of rate limiting you at whatever, 25,000 IOPS in this particular, that's a lot of IOPS, but instead of rate limiting you at that maximum and having really high latency, if you do have those credits, you can burst above and get that transaction out of the way. And then if you still want to go above your maximum, we will reel you in once you've expended all those credits. Or you can drop back down to your, below your maximum and just keep on accruing them.
So it's not like a client decision of.
Oh no, absolutely no, exactly. So the client would not know. Typically, what happens in a system, the really unique feature for SolidFire is that minimum number and the burst. The minimum is an extremely hard thing to guarantee, and definitely our all-flash architecture enables us to do that. But that doesn't mean that any all-flash architecture is going to do that. As far as I know, we're the only system that does a minimum guarantee. Maximum is common, where people will rate limit you. They will just give you a hard limit. You can't go above that. That is not very flexible, and so that's why we have this option of bursting above the maximum, which is pretty useful in bursty workloads, which is, for most people, that's the majority of their workloads. Yeah, maximum, I kind of refer to it as sort of like rate limiting, but then I always have to throw that caveat of burst in there, because rate limiting by itself, to me, isn't really a great thing. It's easy enough to do, but it's not really very flexible.
How are you getting that minimum? Because at some point you're going to saturate.
Well, it depends how much time. But what we do is, so let's say you got your cluster, whatever, 20 nodes or something like that. The data that comes into the system is going to be written to NVRAM on one node, and then we have another node it's going to be written to. It's going to be written to NVRAM, and then every single node in the cluster is going to be responsible for a certain number of volumes. So the I/O load is distributed across the cluster as well as the capacity. And then we keep track on the back end as well if we need to migrate volumes to another node to make sure that we can maintain performance guarantees. So there's basically capacity load balancing and I/O load balancing going on in the system all the time. Yeah, typically what'll the writes will always go to NVRAM. They'll be duplicated to another node. Then they'll be acknowledged to the host, and then they'll be flushed out in the background to the SSDs, and they'll be stored on different boxes, but different, whatever you want to call them, different nodes, different storage servers. And that way too, if any one node goes offline, all of the data that's on that node is elsewhere in the cluster. And then we will regain redundancy quickly, to make sure there's not going to be a double fault. Cool. Anything else? I like the questions. That's good. I'll have you out of here by 8 o'clock. Okay, my plane doesn't leave till midnight. So, all right. We got this one here. And actually, I guess I'd like to point out too that the SolidFire GUI, it's not really used a whole lot because the system itself was really built around automation at every step of the way. So we have me full-time on CloudStack automating that. We have another guy full-time on OpenStack automating all of that, all of the various VMware products. We're tied into all of these other products, and then it sort of transparently works with the SAN. You can definitely go into the GUI, you can check things out as you sort of need to, but it's sort of not like routine that you would necessarily go into the GUI. You would probably do a lot of these things through CloudStack or OpenStack or VMware or whatever. And then the GUI itself, it just sits on top of the API that I use in CloudStack. So there's that REST-like API, the GUI uses it, I use it in CloudStack, our OpenStack guy uses it, our VMware guys do it. So we consume the same thing that our customers consume if they want to access our SAN as well through its API. All right, cool. So we got our volume, we got our large LUN in this world. All right, it's a little hard to see here, but this is actually going into Zen Center and then consuming that volume, that LUN, as an iSCSI storage repository. So that top left is really, I've gone in, I've said I wanted a new storage repository. I've selected software iSCSI for the storage repository options. Let's see, I guess it goes to the top right. You stick in the IP address of the SAN. So in our case, I've mentioned it's a collection of loosely coupled nodes. So what IP address am I talking about here? Well, in our case, we have a management virtual IP address, what we call a MVIP, and a storage virtual IP address. So when you send commands to the SAN like create a volume, take a snapshot, make a clone, they go to the management virtual IP address. And any one of those nodes can host that. And if that node goes offline, let's say you're upgrading the cluster, you're doing a rolling upgrade, it's time to reboot that node, the new software has been installed. We reboot that node, it's hosting the MVIP. One of the other nodes will pick up on that and grab the MVIP and continue to respond to commands. And it's the same concept for the storage virtual IP address. One of the nodes, so when you do an iSCSI login, you're going to talk to the guy who's hosting the storage virtual IP address. He's going to say whether or not you can log in, and then he's going to load balance the connection to one of the other nodes in the cluster, unless, of course, it happens to be his turn. But it's basically an iSCSI redirect to another node in the cluster. So that way the I/O is balanced across the cluster as well as the capacity. And then, of course, if a node goes offline, we're going to redistribute the iSCSI connections that got dropped as they come. They're going to basically go, if a host got dropped, he'll go talk to the storage virtual IP address again, log in, and he'll get redirected to another node. It may not be the same node if the other guy's offline. It's all just transparent to the hosts. Yeah?
Do you strive and mirror the data in one node or replicate it to other nodes, or how you backup your data?
Sure. So when the I/O comes in, we're going to go to whatever node you're talking to. So if you got your 20 nodes or whatever, 100 nodes, you're talking to one of those guys. You write some data. He'll have like a secondary, one of those other 20 or 100 nodes, where he'll replicate the data to, and that'll be in NVRAM. So now you've got your data in two places in NVRAM. Once that's happened, we'll acknowledge the write back to the host, and then in the background, once we've kind of aggregated our writes, we'll flush them out to the SSDs, and that data will be distributed evenly across the cluster. And pretty much, one of the cool things here too is if you write the same data anytime, doesn't matter if it's same volume, different volume, there will just be two copies of that data in the cluster. So it's deduplicated cluster-wide. So now, really what happens, I kind of skipped a step there. The data comes in, we hash it, and we take the data and we compress it. And then we kind of have like a key value concept as far as like accessing that data. But it's compressed right away, and then it's sent to the other node, and it's in NVRAM on both nodes. And then it'll be sent to the SSDs in larger chunks, basically, so we can use our log structured file system to basically treat the SSDs friendly and write a whole bunch of data at one time, and then just kind of in a rolling sense, we go back and see like which data is in use. If you're in use, we're going to rewrite you to the front of the log. If you're not in use, we get rid of you. So.
And how does the hash and compression works, those performance? Does it affect it? Or?
So there's a lot of horsepower. These are all industry standard boxes, but I don't know how REAC works with this. I think REAC is pretty much like just grab whatever hardware you want and make sure it works. We definitely sell like a a small, like we have like 4 or 5 models of hardware that we sell. And we make sure that we spec it. It's all industry standard from Dell, but we definitely make sure that we spec the hardware out. When we sell the product, it's on hardware that we know we've tested for performance and everything. Yeah, yeah. You can be a little bit more flexible with secondary storage, and I'm sure that's why REAC can do that. But for primary storage, we definitely have to make sure that we can meet those performance guarantees that we say we can meet. And the only way we're comfortable doing it is by making sure that we spec the hardware ourselves and test everything in our own labs. So cool, that's what that top number is, or IP address. That's the storage virtual IP address. So the hypervisor is going to use that to log into the volume. I don't know if you use CHAP or if you don't use CHAP. Those are some of the other fields you can fill in when you create a storage repository. And then at the way bottom, that's just picking the iSCSI target, and then within that iSCSI target, the LUN. In our case, there's only one LUN per iSCSI target, so you'll just see LUN 0. Once we've done that, come over here. We're just going to give the storage repository whatever name you want. It's hard to read, but it says SolidFire_gold, and that'll come into play in a slide or two in the future. And then at the very end there, we can see bottom right, we've got our new storage repository. I think it looks like, yeah, it's at the same level as the hosts, which just sort of graphically represents that it's shared storage between the hosts, versus there's a couple other storage repositories there, but they're local, and they're right under their hosts. So just within Zen Center, they just sort of graphically represent shared storage at the same level as the hosts and within the pool, the compute pool. Cool, so now we've got our storage repository. So just kind of, I guess we were on a little bit of a tangent there, but we made our large volume on the SolidFire SAN. We made our storage repository in Zen Center, and now it's finally time to come over to CloudStack. And if it seems like this is taking a while, that's probably a good thing because it's just sort of illustrating the fact of how static and can be sort of tedious to go through this process, and then how it gets automated once we hit the 4.2 release. Now that we're in CloudStack, we can go into the Infrastructure tab. There's a primary storage section. In the, see, this is the top left picture. In the upper right, there's an Add Primary Storage button. So I guess just to point it out, there's only 2 primary storages right now, and both of those are the local storage of, I just have 2 Zen server hosts in my cluster. So we've got 2 local storage repositories that were just automatically consumed by CloudStack when we added those hosts. On the far right, we've got our dialog to let us create primary storage based on this Zen server storage repository. We just pick a zone, pod, and cluster. So remember, this kind of primary storage exists only at the cluster level. So we've got to be real specific here, zone, pod, and cluster. It's only going to service the hosts in that particular cluster. Give it whatever name you want. I don't know why I put an IP address in there. I think at the time I only had 1 host in my cluster and I just named it that, but pick whatever name you want. The protocol, there's a couple options when you're dealing with Zen server. In this case, I used CHAP credentials, and CloudStack doesn't actually support CHAP credentials if you want CloudStack to make the storage repository for you. So what I did here was I said a pre-setup for the protocol. That just means that I manually went out and created the storage repository, and I'm just going to give you its name, and then you're going to consume it. If I actually didn't need to use CHAP credentials, you can pick iSCSI as the protocol, and then there's a few other fields that'll show up, and you can fill those in. So it's a little bit more convenient working with Zen server. These kind of options aren't necessarily as prevalent in CloudStack for vSphere and KVM. But in this case, I did use CHAP credentials, so since it's not supported in CloudStack, I picked pre-setup. Then I put the SR name label, so that's that SolidFire_gold. When we were back on the previous screen and I put in a name for the storage repository, that's the name. And then right below it is the storage tags. So this is something I kind of alluded to earlier. This is my way of describing this primary storage. And I guess to be a little bit clearer, I probably should have just used a different storage tag name than the name of the SR. But it doesn't have to be the same as the SR. It could be, like I said, it could be as simple as fast, SSD, super duper slow, whatever you want to use to describe this. You might have different compute and disk offerings. Maybe some of them are going to be placed, they're going to be more expensive, and they're going to be placed on faster storage. Other ones, they're going to be cheaper, could be placed on slower storage. So this is your way of describing the primary storage. And it's not confined to a single label. You can separate it with commas. It's actually nicer in the 4.5 release, where we have a little bit more sophisticated control. I've never liked this because you have to know to separate things with commas, and then when you use it from the compute offering or the disk offering, you have to try to remember what the storage tag was. And it's much nicer in the 4.5 release, where whatever you stick in here, whatever storage tags end up in the database, when you're in your compute offering and your disk offering dialog, you can just kind of like type in, oh, I know it starts with an S or whatever, and then it'll give you a list of all the storage tags that have the letter S in them, and so you can just pick it. But right now, in this particular screenshot, everything is just comma separated. You just gotta make up some labels that describe your primary storage. If you want more than one, just separate them by a comma. And then we're going to use these in a little bit when we make a compute offering and a disk offering, I believe. So once we hit the OK button, we obviously have our new primary storage here. So the top two rows, that's our local storage repositories. And then the bottom one is our shared. Okay, any questions? Are we talking a SolidFire question here, or is this a? Okay. Okay, and what was the
limitation of the numbers?
how many primary storages?
Yeah.
I remember asking that when I first started in on CloudStack a couple years ago. So this information here is mainly just stored in CloudStack's database. The actual difficult part is on the hypervisor and the storage system to actually keep that storage up and running. So no, you can pretty much just add primary storages to your heart's content. Yeah, at least I've not seen any kind of a limit. There's no hard limit in CloudStack, let's put it that way. Yeah. And a lot of these will be distributed. If you have multiple clusters, this cluster will only be concerned with storage, primary storage X, Y, and Z. That guy might be primary storage A, B, and C. So he's really only concerned with those three. This guy's concerned with his three. And CloudStack pretty much just knows how much capacity and IOPS now have been sucked up from those different storage pools. So when the time comes to spin up another VM, it might look and say, well, I got the capacity here, but I don't have the IOPS. Well, how about over here? Oh, okay, I got both. Let's spin up the VM in this cluster. And then the end user doesn't have to worry about that kind of thing. Yeah, cool. All right, great. All right, moving along. Now, we've got our primary storage. The time has come to make a compute offering. So the compute offering, again, that's just a template that describes the characteristics that we want for a VM that we spin up. Most of this stuff I won't really focus on too much because there's only a little bit of storage involved in this. But you give it a name, a description, the storage type. This is helping CloudStack decide, is it going to be shared storage that this root disk has to be on? When I say root disk too, I just like a bootable disk. I think a lot of times in CloudStack we tend to use the term root disk, but a lot of times people have asked me, is that a bootable disk? Yeah, that's a bootable disk. So the storage type, I guess that says shared or local. You have those two options. You just have to pick one or the other. If you do not put in any storage tags, then that's all CloudStack has to go off of is local or shared storage, which is totally fine. But you can further refine that at the bottom by specifying storage tags. So we made our primary storage, and we gave it the storage tag of SolidFire Gold. So now I'm just going to use that. I'm just going to say, when you spin up a VM, I want its root disk on primary storage that describes itself as SolidFire Gold. Right now, we just got the one primary storage that has that. In a larger environment, you might have dozens that have that storage tag. And so that'll be for CloudStack to decide. That's one constraint. There could be other constraints as well, as we'll see later. I don't have the IOPS in this particular. This is, again, this is sort of like pre-4.2, so there was no concept of IOPS and that sort of thing. But in this world, pretty much we're just looking at the capacity and where can we put that root disk. And that's going to give us, it's going to give CloudStack guidance. It's got to be on shared storage, and whatever shared storage we pick has to have SolidFire Gold as a storage tag. Cool. And all right, and really it's the same thing for disk offerings. So there's compute offerings. That's for your VM template, like how many CPUs, how much memory, where should the root disk be placed. And then there's disk offerings, which is more like for data disks. I didn't really go through an example there with disk offerings. I do have one coming up. But just kind of know that there's this thing, generally speaking, we call them service offerings. And then underneath that, you have compute offerings, disk offerings, and then sort of unrelated stuff to storage, you have like network offerings. This here, sort of like transitional slide between kind of this older, more static model of storage, and then kind of where I'd like to continue taking it in the future. We've started with 4.2, 4.3, and 4.4. On the left up here, that's kind of what we just saw. So traditionally, people might have some kind of storage pool. Maybe it's under some kind of RAID configuration. And then they carve out LUNs like what we did. They'll take that LUN over to their hypervisor. They'll consume it as a storage repository, if it's Zen Server, data store, if it's vSphere, and then they'll bring it into CloudStack. And then once they do that, you'll have that primary storage layer with your storage tags, and then your service offerings, your root disks and your data disks, are going to share that LUN. And as we mentioned, that's not very ideal from a quality of service standpoint, but it was fairly simple to implement. And so now we kind of want to take that a step further, which is on the right side there. And I won't go through all the little boxes, but really it's just saying we want a one-to-one mapping between a root disk and a back-end volume. And then ideally, with a system like SolidFire, you can pick minimum IOPS and that sort of thing. So every time you spin up a VM, it needs a root disk. The back-end volume doesn't actually exist until you spin up the VM. And then through the plug-in mechanism, we go off to the back-end, we create that back-end LUN with the appropriate capacity and IOPS, and then we give it back to CloudStack, which gives it to Zen Server. Zen Server now knows how to create a storage repository automatically for you on that new LUN, and then CloudStack will put the root disk, or if this is a data disk, on that storage repository. So really that root disk or data disk will be the only disk, I should say it's the only virtual disk on the back-end volume. And if you have a guaranteed number of IOPS for that back-end volume, then it just stands to reason that you have that guaranteed number of IOPS for that one virtual disk. Does that kind of make sense? Oh, so you mean like the IOPS size? So you can definitely, most applications do kind of throw a variable sized, like a variable sized.
I'm writing a video.
I'm sorry, what was that?
A video or an image with 2 megabytes on size.
Okay, so the VDI?
How big, how much transaction you can support? You know, you're saying you support 1,000 IOPS
Right, yep.
per second. Is there any limitation on the size of those?
Oh, so that's a good question. So what actually happens there is when you picked those IOPS, because I know IOPS by themselves, they don't really specify the size of the I/O. Exactly. So you're not really confined to the size of the I/O, but probably ideally what you would have done ahead of time is get a feel, maybe using something like VDBench or whatever, just to get a feel for what's your average I/O size, and then you can pick the IOPS appropriately and if you're wrong, that's okay. You can still go back later through CloudStack or the GUI, or if you just like to use the API, and you can change that. Yep. And that doesn't lead to any kind of data migration or anything. It's just sort of within a few seconds, you should see that the additional IOPS at your disposal. So, I mean, it still works really well with multiple virtual disks on the same SolidFire volume. I mean, you can look at that and see like, well, you know, we're always running at maximum. Well, let's bump up the IOPS to that. And that will help out those virtual disks. So I could really see, because there are currently LUN limits in a lot of hypervisors. So I think, and I'll have to talk to Tim about this later, but just to give an example for like, I want more than, yes, right now actually what happens is I would love for every single root disk to have its own backend volume, every single data disk to have its own backend volume. I mean, obviously the SolidFire SAN can handle creating all those volumes, but a lot of times what happens is the hypervisors have limitations in terms of how many they can consume in their cluster. So VMware, for example, has this big vVols initiative that they've been working on for years, and hopefully it's supposed to come out, I think, Q1 next year, where they'll actually, not just every root disk, every data disk, but every config, any file that they write in their data store right now, they want that to be a separate backend volume. And right now, they would be overloaded with that many LUNs. They can only really handle 256 per host. But it gets kind of worse, because if it's a shared LUN, then it doesn't matter if host 1 is the only guy using it, the other guy's got to see it too. Yeah. So with vVols, they'll be able to explode that number. And then I've been chatting with Tim in the back there about similar things for Zen Server. Yeah.
So is redundancy built in, or is it something I have to manage? If I want multiple copies, is that part of the input, or is it just copying back?
So do you mean like when you, like the data that you write out to your backend volume?
Yes.
So that's going to be two-way replicated. You don't have to worry about, basically when the data comes in, it's going to get hashed. And then based on, yeah, it'll get hashed and compressed. And the hash algorithm, I think it's a 16-byte hash code that it comes out with. And I believe like the first 2 bytes indicates, based on the current state of the database, where in the cluster that data is. It's called content addressing. And so that will determine where the data gets. It's going to be in 2 places. Yeah. So it doesn't matter which volumes write that data. So you could figure the most commonly written sequence of bits is really 0. That will just be in 2 places in the cluster.
Oh, sorry.
No problem. Oh, that's fine. Yeah, yeah. I forgot what I even answered before. Okay. Like I said, you're going to be here till 8 o'clock. So no problem. So yeah, so basically LUN limits right now make it such that most of my customers, they actually use a hybrid approach. They have compute and disk offerings that they offer at a higher price that have dedicated IOPS. And there you have a 1-to-1 mapping. And then the other ones, they'll put on this more traditional model. But as the hypervisors kind of catch up to this, I'd like to get everybody over to the right side. Now, some workloads just don't require it. I mean, and that's totally fine. They can live over in that left area and have a cheaper service offering. But one of the big things stopping adoption of the cloud is people being a little bit afraid of bringing their mission-critical applications into a cloud because of performance variability. So right now, I think about 10% on average of people's workloads are run in the cloud, and most of them are not like mission critical because they don't trust performance.
Security, when you're saying hashing, are you hashing the data? Like
The data that comes in, yes. So
it's always encrypted.
yeah, it's also encrypted on the drives itself. Yeah. So there's, yeah. I think it's AES or something. I'm not exactly sure on that one. Yeah. Oh, I got 5 minutes. Okay. All right, I better go fast. That's okay. The rest of this is easy. Did you have a question? Did I hear something?
You answer.
Oh, did I? Okay, good. All right, cool. So we'll skip over my specific needs for a plugin. I just need to be able to do some of this cool QoS stuff in CloudStack, and I need the system to be flexible enough to permit it. This we will not dwell on. This is just what one of the REST-like APIs looks like to CloudStack. The only thing I wanted to point out is that a couple new fields were added in the 4.2 release. You can specify a provider. In this case, the ampersand is really, this is just one big sequence of text. So SolidFire is the name of the plugin that I want utilized for the primary storage that I'm adding. So in the past, there was no concept of plugins, so that field did not exist when you added primary storage to CloudStack. And now that we have plugin support, we just have to have an extra field that says, hey, for this primary storage, I want you to use this plugin. The default behavior has been wrapped up in its own like default storage plugin. So if you don't specify a provider, you'll get the default provider. Things like this. I love that this is in bytes and not gigabytes. That's 2 petabytes. So you can specify like how much of, in this case, I'm not giving you a pre-allocated volume. I'm giving you a subset of the SAN. And so I'm saying you can use up to 2 petabytes or 4 million IOPS. And so CloudStack will keep track of that as you spin up VMs and you say, I want this. This is really, the 4 million IOPS is really a limit on the sum of your min IOPS. So if you spin up a bunch of VMs and you have min and max, we're really looking at the sum of the mins. Because the max is not guaranteed. The min is what's guaranteed. Rest of that we're just going to skip for the sake of time, and it isn't really that critical. All right. Couple things to point out here. So this is primary storage that's been added to CloudStack that's based on the SolidFire plugin, which means it's at the zone level for one, as opposed to cluster. So that's pretty cool. And then the other thing is that it's not actually representative of a pre-allocated volume. It's representative of a subset of the SAN. Really, that line is saying, it's giving me the management virtual IP address, the storage virtual IP address, how many IOPS I can use, how much capacity I can use. I'm at the zone level, stuff like that. As opposed to, this is a pre-allocated LUN of this size. Excellent. Moving on. So creating a disk offering. So before we made it a compute offering, it's really very similar for disk offerings. A disk offering really is what a user would execute to get another volume that they can attach to their VM. So whatever, SQL Server or something might have a data disk for its logs and other things. This is a way of creating extra volumes to attach to your VMs. The only thing I really wanted to point out here is, I don't know, maybe I have to come off. I'm coming off stage. All right, min IOPS and max IOPS. And there's this custom IOPS up there. Whoops, that was really loud. Uh-oh. All right. So there's custom IOPS, there's a checkbox. That's very much like the custom disk size, which is also a checkbox at the top. So typically, if, I don't know, if you trust your users enough, which might be the case in a private cloud, you might check the custom disk size. And as an admin, you're saying, well, I'm not really going to specify the size of the volume. I'm going to let my end user pick the size of the volume. I have just an analogous concept with custom IOPS. So you can check the box, and then let your end user actually fill in the minimum and the maximum. And like in a public cloud, that's not going to be a great idea probably, but in a private cloud environment, that's perhaps okay. Most of the time, people are not going to check those boxes. They're going to specify the size of the volume, and then they're going to specify the minimum and the maximum IOPS. Burst, we had a little bit of discussion. You got to remember, CloudStack is I got 1 minute. Okay, let's just skip the whole burst thing. That's, anyways, you can specify minimum, maximum. We're going to calculate the burst. I actually want to stick that in later, but I need to do it in a more generic fashion. We got to remember that CloudStack is it's an open source project, and I can't have everything like super duper customized for SolidFire. So right now I just have minimum and maximum, even though SolidFire is the only one that uses minimum. Other people do use maximum because that would be rate limiting for them. Okay, you've either specified the IOPS or you said the end user gets to specify them. Shows up as a normal disk offering would. It tells you what IOPS you have for this disk offering. So when somebody executes the disk offering, this is the number of IOPS they'll get. I'm just going to move on forward. This is an example of creating a volume and specifying a disk offering. So in my case, the one that's kind of in the middle, so I've hit the add volume button, then I've gone to the middle. In this case, I've picked a disk offering that the admin specified the size and the IOPS. In the far right, I've picked a disk offering where the admin actually let the end user pick the IOPS, but not the size. You can actually have them pick the size, the IOPS, or both, or none. None is the most common, that middle one. Okay, cool. Attach it to the VM. What happens on the SolidFire SAN? You have now created a volume automatically on the SolidFire SAN, so we never had to see the GUI. It's a pretty looking GUI, but we didn't have to go into it. You've got your IOPS, you've got your size. On the hypervisor side, you didn't have to go into Zen Center and configure a storage repository. CloudStack did that for you. And then you can see in the far right, there's a virtual disk, which is representative of our data disk. And that guy should be the only virtual disk in that storage repository, short of you doing things like hypervisor snapshots, which it's like a parent-child kind of deltaing scheme. When you take a snapshot, the parent contains the data, and then the child sort of is a new VDI, which is going to collect the new writes. But that all is representative of the same virtual disk. So even though you would see multiple VDIs in the SR, they're all representative of the same virtual disk. Let's see, I think I probably have about 2 seconds, so let's see here. Oh, great, a lot of text here. This just really specifies, and these slides I imagine are going to be online, but it just specifies, this is really like a phased project. It's a huge amount of work adding quality of service and getting all of this implemented in CloudStack. And so in 4.2, I didn't do everything is all this is saying. This is saying what I did in 4.2, in 4.3, in 4.4, what I'm doing in 4.5 right now, and then right now we're actually also working on 4.6. So unless anybody really wants me to go through these in detail, I'll leave this as an exercise for you. And I think I just have one more, which I will not go through because it's really a lot of text. So does anybody have any questions? Oh, great, thank you. Thank you. All right, well, I will not keep you till 8 o'clock, but thank you.